All right, good morning, everyone. And yeah, if we can settle down, we'll start our lecture on this Monday morning. I hope you had a good weekend. We'll do lecture 7 today. As the title intuitively says, today we will learn how to analyze circuits that contain resistors. And our task for today is to be able to determine the voltages and the currents in the resistors in a circuit. And it sort of carries on from what we've learned in our last lectures. In our last lecture, we already learned how to simplify circuits, right? We learned that when you have resistors that are connected in series, as shown in this figure here, series again is when your resistors are connected one after the other. There's only a single pathway for the current to flow. Then the idea is that you're able to reduce this series combination into a single resistor. And the value of the resistance of that single resistor is the sum of the individual resistances, right? And then if the resistors are connected in parallel, as shown in this figure here, and again, the distinguishing feature of a parallel connection is that you have a junction where the currents can divide. The current then passes through each of the resistors after dividing, but one junction is not enough to identify a parallel connection. You need to have a second junction where the currents that originally divided combine. So you have two junctions in essence, one junction where the currents divide, let me see. Yeah. And another junction where the currents then recombine after passing through individual resistors. And if your resistors are connected in parallel, also the key idea is you are able to reduce this parallel connection into a single resistor. And the value of that single resistor is obtained by adding the reciprocals of the individual resistances. So in this format here, you have to take the inverse after adding the reciprocals, or equivalently, you add the reciprocals or the inverses, and then take the inverse of that to get the equivalent resistance. So we had some practice, well, I hope enough practice in the workshop last week. And if this still confuses you, then I would highly recommend to book a time and see me, because today's lesson highly depends on the ability to reduce series and parallel connections into a single resistor. Because today's lesson hinges heavily on reducing the circuit into a single resistor, let's do a little bit of practice. You have here 3 resistors connected as such. Okay, we want to reduce this into a single resistor. So which resistors do you combine first? Is there an obvious connection, series or parallel, that you can readily or easily combine into a single resistor? Anyone? You can always put a dummy current to try and identify connections. Yeah, if you put a dummy current through point A, okay, that current passes through R1, just passes through R1, all of that current. Then it encounters this junction where the current divides. The divided current goes through each of the 2 kilo ohm resistors, and then that current then combines at this second junction here. Right, so you have 2 junctions, these 2 junctions defining this parallel connection between the two 2 kilo ohm resistors, right? So R2 is in parallel with R3, hence right? The equivalent resistance of the parallel connection is adding the inverses of the individual resistances that are in parallel and then taking the inverse of that. So 1/2 plus 1/2, that effectively gives you 1/1 kilo ohm inverse. Hence, the parallel connection can be reduced into a single resistor whose resistance is 1 kilo ohm. Okay, so essentially your circuit can be redrawn if you want. And I suggest, especially if you're just starting out, I suggest redrawing the circuits. Right, that's point A there. Originally, you have the R1 resistor, and then you have this junction. These two parallel resistors can be replaced by this equivalent parallel resistor resistance of 1 kilo ohm as you have calculated, right? And you have, of course, here junction B. So by redrawing the circuits, replacing these two resistors, you can now see that R1 is in series with R parallel, the combination of R2 and R3, because you have now a single pathway where the current will pass through. So R1 is in series with R parallel. Okay. Right, and if you have resistors in series, you can get their equivalent or effective resistance of the series connection by adding the individual resistances. So just R1 plus R parallel, you have 3 kilo ohms plus 1 kilo ohm, 4 kilo ohms. Effectively, you have now reduced your connection into, so that's point A and that's point B. Between points A and point B containing these three resistors, you were able to simplify that into a single resistor R equivalent, whose resistance is 4 kilo ohms. Good. Right. Okay, happy with that solution? So now our task for this lesson is to try and find the current through each of the individual resistors. What's the current through R1? What's the current through R2? What's the current through R3? And also, what is the voltage across each of the resistors? What's the voltage across R1, across R2, and across R3? When we're doing voltages and currents, some fundamental concepts you need to remember, and you already encountered these concepts in the last lecture, but just for a reminder, if your resistors are connected in series, okay, the currents through each of the individual resistors should be the same because there's only a single pathway for the current to flow. So whatever current flows through R1 will be the same current that flows through R2 and also through R3 if these resistors are in series. Okay. And in terms of voltages, when the resistors are connected in series, the voltages add up. So the voltage across R1 plus the voltage across R2 plus the voltage across R3 will be equal to whatever, voltage. This will be the voltage across the series connection, right? So in series connection, the voltages add up, but the currents are equal. And for parallel connections, because you have a junction where the current will divide, then the current passing through each of the parallel resistors should add up to be equal to the current that went inside the parallel connection. So this is essentially I parallel. And this is also I parallel. So whatever current comes into a junction will divide into the individual currents passing through each of the resistors. but then those currents will combine at the second junction to equal the current that came into the first junction. So currents add up in a parallel connection, but the voltages are equal in a parallel connection. Okay. So these are important concepts that you have to keep in mind as you analyze circuits and trying to find the voltages and the currents in each of the resistors in the circuit. Okay. And of course, the fact that we can reduce resistors into a single resistor. The first step, if you're trying to find voltages and currents, if it's possible, the first step is to simplify the circuit into a single resistor. Okay. And that's why we first learned how to simplify connections of resistors into a single resistor, because that's the first step that you need to do. And then you apply these concepts for parallel and series connections after simplifying your circuit. All right, I think the easiest way to understand this and how to learn how to analyze a circuit is to practice. So let's go through this example step by step to see what I mean by first simplifying the circuit into a single resistor and then applying the relationship for currents and voltages in series and parallel connections. So here you have the 3 resistors in the configuration you saw in the earlier slides, but this time we connect the resistor connections to a voltage source or a battery, an 18-volt battery. Okay, positive terminal is indicated by the long side and negative terminal, of course, by the short side. We want to calculate the voltage across each of the resistors and then the current through each of the resistors. Before we go to the calculation, I'll just define some terminology that you might encounter, right? We want to calculate the voltage across each of the resistors. And often in a circuit, sometimes you will see points that are indicated in the circuits. In this circuit, you can see points A, C, and B, as shown by dots here. If we say we want to calculate the voltage across the 4-ohm resistor, we're essentially wanting to find the voltage here. We're essentially wanting to find the voltage across points A and C. Okay, so the voltage across the 4-ohm resistor is also equal to the voltage across points A and C. So voltage subscript AC. Similarly, if you want to find the voltage across the 6-ohm resistor, we can use the notation voltage CB, meaning the voltage across the 6-ohm resistor is the same as the voltage across the points C and B. Okay, so of course, the voltage across the 3-ohm resistor will also be the voltage across point C and B. Okay. And as we learned, the 3-ohm resistor and the 6-ohm resistor, they are in parallel, so their voltages should be equal. And that will be the voltage across point C and B. All right, we okay with that notation? So regardless of whether you encounter in the questions, in the assignments or the tests, whether you encounter this notation, VAC, or voltage across whatever resistor there, right? They mean the same thing. So just be aware of points indicated in the circuit right there. Okay, so let's proceed and analyze the circuit here. So usually when you're given just a single voltage source and some multiple resistors, usually you can always simplify the resistor connections into a single equivalent resistor. In our lecture tomorrow, we will learn about what if you cannot simplify the resistors into a single resistor, right? But today, right, And as I've mentioned, usually if you have a single voltage source and multiple resistors connected together, more often than not, you will be able to simplify these resistors into a single equivalent resistor, right? And yeah, so let's do that. Okay, as this is very similar to the configuration we've seen earlier. So 6 ohm is parallel to the 3 ohm resistor. Okay, the equivalent resistance of the parallel connection is 1/6 plus 1/3. And taking the inverse of that, that's 2 ohms. Okay, when you redraw your circuits, include the battery, because then it will make you visualize the whole circuit all together. You have the usual 18 volts as provided. You have the 4 ohm resistor. You didn't do anything with that 4 ohm resistor. You only manipulated these 2 parallel resistors. They have an equivalent resistance of 2 ohms. Right, so these 2 resistors, they are in series. 4 ohm in series with the parallel resistor. So you have the equivalent resistance is 4 ohms plus 2 ohms, 6 ohms. And again, I recommend to redraw the circuits and include the battery in your drawing. You now reduce your circuit into a single resistor with a resistance equivalent to 6 ohms. All right, be happy with this simplification here, right? So once you've simplified your circuit, as you can see, you're now down to the circuit with 3 resistors, to a circuit which is the simplest circuit that you can have, 1 voltage source and 1 resistor. That's the simplest circuit you can have, right? 1 resistor and 1 voltage source. Right, and hence if you have this simplest circuit, so it's the same circuits here, I just redraw it here, you can then calculate the main currents. Okay, so from this circuit here, we can calculate the main current in the circuit using Ohm's law. Okay, and that's the whole idea of why we wanted to simplify these 3 resistors into a single resistor, because the objective is to achieve this simplest circuit, which contains a single battery and a single resistor, because then we can easily apply Ohm's law. V is equal to IR. Okay, rearranging that, the current is equal to, the main currents in your circuit is equal to the voltage of the battery or the voltage source divided by the equivalent resistance. Okay. Right, voltage of the battery, 18 volts divided by the equivalent resistance we've calculated from before. Hence, you have a 3 amp current flowing through the whole of your circuit, right? From the positive terminal to the negative terminal of the battery, you have a main current equal to 3 amps. All right, good. Once you've calculated the main currents from your simplest circuit, you then work your way backwards. Yeah, so once you've done that, you sort of work your way backwards through the circuits that you simplified. So you can see that this 6 ohm equivalent resistor actually consists of 2 resistors that are in series, right? This 6 ohm effective or equivalent resistance came from this previous circuit, which consists of a 4 ohm resistor that is in series with this R parallel resistor. And what did we learn about resistors in series? The currents, which is the same. The currents should be the same in series, right? So that means that if 3 amps current is flowing through the 6 ohm resistor, then that means it's also the main current that's flowing through each of these individual resistors that are in series. So that means this should be equal to the main current so through each of these series resistors, the current is 3 amps. So, and hence you are able to find the current through the 4 ohm resistor is equal to 3 amps, right? Which is the current, the main current flowing through your circuit, and the current through the R parallel resistor is also 3 amps. Good. Does that make sense? Yeah. Right. Okay, so just working on this circuit here, we've now determined that the current through the 4 ohm resistor is 3 amps. The current through the R parallel resistor is 3 amps. Once you know the current and the resistance, then you can calculate the voltage. Ohm's law only requires you to know 2 variables in order to calculate the third variable. We already know the current and the resistor in the 4 amp resistor, so we can then calculate the voltage across the 4 ohm resistor is equal to the current through the 4 ohm resistor times the resistance of the 4 ohm resistor. All right, so the current through the 4 ohm resistor, that's 3 amps, times the resistance is of course 4 ohms, so the voltage is 12 volts. Right, and you also do the same thing for this parallel resistor, R parallel. The voltage across the R parallel resistor is equal to the current through the R parallel resistor times the resistance of the R parallel. Okay, the current is 3 amps times the resistance of the R parallel resistor is 2 ohms. So that's a voltage of 6 volts. Right, you can check whether your answers are correct for the voltage, because you can see here from your redrawn circuit that the 4 ohm resistor is in series with the R parallel resistor. So to check, okay, we know that in series, voltages add up. And therefore, the voltage across the 4 ohm resistor plus the voltage across the R parallel resistor should be equal to the voltage of the battery or the source. Okay? And if you do this check, you've calculated that the voltage across the 4 ohm resistor is 12 volts. And the voltage across the R parallel resistor is 6 volts. Okay, and indeed 12 plus 6 is equal to 18 volts, which is the voltage of the battery as given in the circuit. Good, happy with that? Right, so we've now, so I'll use a fresh page, but what we have now determined is the current through the 4 ohm resistor, that's also equal to the current through the parallel resistor and the voltage of the 4 ohm resistor. So we've already calculated the currents and the voltage of this 4 ohm resistor here. We now want to calculate the currents and the voltages for the 6 ohm and the 3 ohm resistor. But what we know is that the voltage across this parallel resistor is 6 volts. Yeah, the voltage across the parallel resistor is 6 volts. We've calculated that before. Now, if you move backwards, you know that the our parallel consists of 2 resistors that are in parallel, and you know that in parallel connection, voltages are the same. So therefore, the voltage across this R parallel resistor should be equal to the voltage across each of the resistors that make up that parallel connection. Right? So therefore, voltage of R parallel is equal to the voltage of the 6 ohm resistor, and that's also equal to the voltage of the 3 ohm resistor. Right? So therefore, that's 6 volts. So each of the 3 ohm and 6 ohm resistors will have a voltage of 6 volts. And hence, V is equal to IR will give you the currents. Once you know the currents or the resistance, you can find the voltage. Or once you know the voltage and the resistance, you can calculate the current using Ohm's law. Right? So the current through the 6 ohm resistor is equal to the voltage of the 6 ohm divided by the resistance of the 6 ohm. Right. So that's 6 volts divided by 6 ohms, 1 amp. Okay, and likewise for the current through the 3 ohm resistor, you have the voltage across the 3 ohm resistor divided by the resistance of the 3 ohm resistor. The voltage across the 3 ohm resistor, that's 6 volts. It should be the same because the 3 ohm resistor is in parallel with the 6 ohm resistor. So that's 6 volts divided by the resistance, 3 ohms. 2 amps. Right? And you can also do a quick check. You know that the current here is 3 amps. So the current entering the parallel connection is 3 amps. It divides, the 3 amp current divides into the 6 ohm and 3 ohm currents. Right? The current through the 6 ohm resistor is 1 amp. And the current through the 3 ohm resistor is 2 amps. In parallel connections, the current should add up. 1 amp plus 2 amps is equal to 3 amps, which is exactly the same amount of current that went into this junction here. And of course, it will be also the same current that goes out of this junction B. So 3 amps of current goes into junction C. It divides into 1 amp through the 6 ohm resistor and 2 amps through the 3 ohm resistor. And then that combines in junction B to 3 amps current, which is also the main current in the circuit. So you can do some quick checks to see if your calculations are correct. Good. Are we happy with the solution or are there any questions? Right, good. Okay, if there are no questions, well, this slide just summarizes what we did there. We first simplified the circuit to a single resistor, calculated the main currents using Ohm's law, and then work your way backwards, calculating the currents and voltages in each of the resistors as you work backwards, remembering that in series connection, the currents are the same, and in parallel connection, the voltages are the same. Right, so that's just a quick guide. If you're happy with the solutions that we did and you don't have any questions, then it's your turn to do this exercise. Yeah, I nicked it off of some of the past years test questions you have here. A voltage source and 3 resistors. And the question is to find VAC, or the voltage across points A and C. And so work on this question. If you want to check your answer, the answer is 3 volts. Yeah, VAC is of course the voltage across, yeah, these 2 points A and C. If you can see in the figure, it's the voltage across the 10 kilo ohm and the 20 kilo ohm resistors combined. Right. Right, so the simplest approach to this is to reduce your circuits into a single resistor circuits. I hope by now it's clear that all three resistors are connected in series. The current has a single pathway going from the positive terminal to the negative terminal of the battery. And hence you can reduce your circuits, right, by adding the individual resistances. 10 plus 20 plus 30 will give you 60 kilo ohms of equivalent resistance. That then allows you to calculate the main currents through your circuit provided by the battery. Main current will be the voltage provided by the battery divided by the equivalent resistance. So you have 6 volts divided by 60 kilo ohms, right? 1 times 10 to the minus 4 amps. Right, so you have current flowing through your circuit. This current I is equal to 1 times 10 to the minus 4 amps. Because your resistors are all connected in series, that means that the current is the same through each, and that same current will be equal to the main current that you've calculated. So current through each of the resistors, current to the 20 kilo ohm resistor, current through the 30 kilo ohm resistor, that's all equal to 1 times 10 to the minus 4 amps. Okay. Right, so you've calculated the voltage, the current. What you want is the voltage, right? What's being asked is the voltage. But once you know the currents through each of the resistors, and you know the resistance of the resistor, it's easy to calculate the voltage because you know using Ohm's law, V is equal to IR, you can calculate voltages. So there are 2 ways of calculating this. The first way is the shortcut. You can directly calculate the voltage across A and C, which is effectively taking the voltage across these 2 points, right? So voltage across A and C, you know that you have 2 resistors across the points A and C. So you need the voltage across A and C will be equal to the currents across the points A and C times whatever resistance there is between the points A and C. But you can see you have 2 resistors that are connected in series between the points A and C, which are the points of interest for your voltage. The current is, of course, the same as the main current because you have a series connection, 1 times 10 to the minus 4 amps, times the resistance between points A and C. You have 2 resistors that are in series, so you simply add the resistances. So that's 30 kilo ohms. Kilo is 10 to the 3 ohms, right? Which gives you a voltage of 3 volts. That's required. Good. Right. The other way is, you can always do the slow and sure way. Once you know the currents of the individual resistors, you can always calculate the, so this is one method. The other method is to calculate the voltage across each resistor, across the 10 kilo ohm resistor, and add that to the voltage across the 20 kilo ohm resistor, right? Because in series, the voltages add up. So the voltage across the 10 kilo ohm resistor will be equal to the current through the 20 kilo ohm resistor, which is the same as the main current, 1 times 10 to the minus 4 amps, times the resistance, 10 times 10 to the 3 ohms. Okay, this will give you 1 volt. Okay, and calculate the voltage across the 20 kilo ohm resistor, right? You have the current through the 20 kilo ohm resistor will still be 1 times 10 to the minus 4 amps, the main current, because all the resistors are in series, times the resistance of the 20 kilo ohm resistor, 20 times 10 to the 3 ohms, will give you 2 volts, right? And these two resistors, the 10 kilo ohm and 20 kilo ohm resistors, they are in series, and they are the two resistors that are between points in A and C. So therefore, the voltage across points A and C is 1 volt plus 2 volts, which is also the same 3 volts that you obtained by using the first method. Okay, but first you really have to find the main current in the circuit. There's no going around finding the main current. That's the most crucial step. And then once you know the main current, you can easily find the resistors, the voltages across each of the resistors. All right, any questions about this exercise or the solution? Or good. Do you think it's relatively straightforward? And yeah, okay. Good. There will be practice, of course, in the workshop. But then, so in this lecture, we just focused on, finding the current and voltages if the circuit can be reduced into the simplest circuit of 1 voltage source and 1 resistor, right? The next question is, what if you cannot reduce the circuit into a single resistor so that you cannot calculate the main current and you cannot work your way backwards to find the individual voltages and currents? And that's what we will learn in tomorrow's lecture when we will tackle Kirchhoff's rules. But if you don't have any questions in this lecture, then I will let you go early. And I wish you a good day and see you tomorrow in the lecture.